So hello dear friends, so let us continue what we have learned in the previous class, which was about the bending stress in beams. So in this session I would like to give some insight about the strength of a beam and how we can design a beam. And I will be focusing on a particular term which is called as a section modulus, which will give us information regarding the strength of the beam. So let us move forward and see what exactly is the section modulus of a beam. In the previous class we learned the bending equation. It's very simple. M by I is equal to sigma by Y equal to E by R, and we know the meaning of each and every terms in the bending equation. It's a very important equation which a mechanical engineer should not forget in his lifetime. So it's having that much significance. Now let us find out the stresses in a beam using the bending equation. So if you consider the first two terms, then we can write the equation for stress as M by I into Y. So the ratio of I by Y, this particular ratio is called as the section modulus, and it is represented by the letter capital Z. So in other words, we can rewrite the equation as sigma is equal to M by Z. So generally, this section modulus gives us the information about the strength. That means if a material is having higher section modulus, means its strength is superior. So Z is a term that corresponds to the strength of the beam. So when somebody asks what exactly is the strength ratios of two particular beam, you need to calculate only, or you need to compare the section modulus. That gives you the characteristics of the strength variation. Now, when we move forward, we have to look into the section modulus of some certain cross sections. And we know that if we take a rectangle, for example, if we take the example of a rectangle like this, then this is going to be the neutral axis. If this is the breadth B and this is the depth D, then we know that moment of inertia about the cross section is nothing but B d cube divided by 12. Similarly, you know the equation for the circle as pi d raised to 4 by 64. So these are the common equations that we use. So here what is the value of y or y max? Y max is nothing but d by 2, which is the distance from the neutral axis to the extreme fiber. So that is nothing but d by 2. Similarly here also y max is equal to d by 2, nothing but the radius. It's very simple. If you are asked to sketch the distribution, you can vary the value of y and you can find the value of stress at any point from the neutral axis. And usually we calculate, or we go only for the maximum value of the stress. This is how we find out the value of Z. If we calculate the Z for this rectangle, we can say that it is B d cube by 12 divided by d by 2. So these two will get cancelled out. These two will get cancelled out. We will end up with B d square divided by 6. That's just for your information, and there is no need to by heart all these things, because bending equation is sufficient for us to solve the problems. There is an additional information that I have given you. Now let us move forward and draw the stress distribution of certain cross sections. This is a very familiar thing. So if we take the rectangular section here, let us draw the neutral axis of all these sections. So let us say that for the L section, this is the neutral axis, and for triangle this is the neutral axis, and for I section, symmetrical I section, this is going to be the neutral axis. This also I will expand a bit more so that we can draw the distribution easily. This also I will expand. Now if we draw the stress distribution of or the bending stress distribution, how it is going to look like? We know that the value of sigma is equal to M by I into Y. We know that the maximum value of M remains constant. The value of I is for the cross section, and that also remaining a constant value. The only variable is the value of Y. That means as the y changes, you have a variation in the sigma. So we have a maximum value of y here at the top position, right? So if we draw a vertical line like this, then here we have a maximum value, and if we draw it like this, this is going to give you the value. This particular section can also be drawn in the right hand side also, no issues. This is just for the compression. So here we can say that this is compression and this is tension. This is one method of drawing the stress distribution of a rectangular cross section. Now what is the next method, or what is the alternative way that we can represent this distribution? See, when we look here, we can say that the top fiber is experiencing a tension and the bottom fiber is experiencing a compression. That means if you take the case of a cantilever, it's something like this. If you keep your palm like a cantilever beam, and if you apply the load, the system is going to bend like this. So if you observe your skin, it's very easy for you to understand the stretching and the compression. The top surface of your palm is experiencing a tension, but when you look at the bottom portion, it is experiencing a compression. That's the same concept is happening in the beams also. So when you consider a cantilever, and when you apply a load, the top fiber is going to experience tension, but the bottom is going to experience a compression. But what is the case for a simply supported beam? What is the case for a simply supported beam? That is the immediate thing we have to discuss about. Okay. Now, when you take the case of a simply supported beam like this, and if you apply a load, it is going to have a sagging effect like this. The system is going to sag like this. So if you observe your palm, you can see that the top fiber has undergone compression, whereas the bottom fiber has elongated. That means the bottom fibers there will be a tension, and the top fibers there will be a compression. So how can we redraw the system? So it's very easy. If you draw it like this, the top fiber is going to experience a compression and the bottom is going to experience a tension. So all together it is going to look like this. It is something like a mirror image. The meaning is same, the value is same, but based upon the nature of compression or nature of bending, we can say which fiber has undergone compression and which has undergone tension. Like that, the distribution diagram will shift. But there is not change in the value because it's purely depending on the value of y. There is no other factor contributing towards the value of sigma. Obviously, there is no other factor is not going to, the m and I value, that is not going to change. So the only factor that is going to determine the variation is y. Okay, now the same is the case for the circular cross section. You have a maximum value here and a minimum value here, or the opposite way, tension or compression. So the same bending stress distribution is applicable for the circular cross section also, because they are symmetric. Both both cross section are symmetric in nature. So definitely the bending stress distribution will be symmetric, and is same for both these two cross sections. The nature is same for both these cross sections. Now, what's the difference when we move from this square or rectangle circular cross section to the L section? What is the difference? So before moving into the L section, let us discuss about the I section. If you look at the I section also, the same observation you can make, because it's symmetric in nature. So definitely it has to be, the bending stress also has to be symmetric. So it can have a value like this. Same thing, everything looks the same, or in the opposite manner like this. These two figures is applicable for the I section also. So if you take the rectangular section, circular section and I section, we can say that the geometry is symmetric about the x-axis, so the bending stress distribution. Now we have to discuss about some unsymmetrical sections like L section and triangular section. So how can we write the or draw the stress distribution of the L section as well as I section? I am not going to give you the exact value of the stress, but how the pattern is, or how the value or how the distribution is going to look like. That's what we are going to focus on. So we can see, if you look this figure cross section, we can say that if this is considered as the neutral axis, so this is going to be the maximum value of y, and this is going to be minimum. That means this will fetch you a minimum value, which can be a tension or compression based upon the nature of bending, and this is going to fetch you a sigma max or minimum max based upon the nature of compression. Obviously, this is the top one is going to be the maximum value. And how the distribution is going to look like? It can be something like this. Here you will be having a maximum, and here you will be having a minimum, and from here, if you stretch it, it is going to give you a distribution like this. Here the bending distribution is not symmetric because the cross section is not symmetric. It can also take a variation like this. From here also it can vary like this. This red color one is, for the red color distribution indicates that the top fiber is in compression and bottom is in tension, and the black indicates that the top fiber is in tension and the bottom fiber is in compression. That's how you have to read these two are two different cases. But these two values, the value which is going to obtain here and here, both are same. The same way of distribution can be observed in the case of a triangle where you have an unsymmetrical cross section. The same thing is, same methodology you use, and you can easily plot the value of stress distribution for a triangular cross section where you have a maximum value at the top and a minimum value at the bottom, something like this. Okay. So the distribution is like this. So just simply by looking into the cross section itself, you can easily predict the behavior, and the magnitude can only be obtained using the equation. That's the only thing you have to keep in your mind. So let us compare the weight of a rectangular to a square and a circular section. So before we carry out such kind of comparisons, we have to define certain relationship between the cross sections. Also, we cannot compare two completely distinct entities. That means you cannot compare a square to rectangle without having any kind of similarities. So that's the two aspects we have to keep in our mind before we start to solve this. So what are the parameters under which we are going to evaluate or compare these three cross sections? So they have given that in the question as they have the same length, they have the same bending load and stress, and made of the same material. So these are the similarities these being have. And what are we supposed to compare? We are supposed to compare the weight. So that's the second part. So let us first discuss how we can utilize these four features to compare the cross sections. First of all, we have to establish some relationship between these cross sections. So let us do that by, this is the rectangle we have, and we have a square like this, and we have a circle like this. So the width is given as B, depth is given as D, and we have a cross section for the square as A, and the diameter is D. So they have given that the stress is same for the square and the rectangle, and we can say that m by I into y of the square is equal to m by I into y of the rectangle. And they have also stated that the bending load is same, so we can cancel out these two values. So what is left with is I by y of the rectangle is equal to y by I of the square. Or in other words, we can say that it is ZR is equal to ZS. So let us compare these two. And the I value of the rectangle is B dq by 12 divided by d by 2. So this is going to give us B into 2b the all cube by 12 divided by 2b by 2. So this is going to give you the value as 2 by third of b cube. Now this is for the rectangle. If we compare the square, we can say that it is breadth into depth cube by 12 divided by depth by 2. So upon cancelling this, we will get the value of a cube by 6. And we know that these two terms are same by the relation. So when we compare this, we will get the value of a cube by 6 equal to 2 by third of b cube. This will give you the value of b equal to 0.63 times of a. This is the relation we are going to obtain. Now we are asked to compare the weight of a rectangle to a square and circular beam. So how will we compare the weight of a rectangle to the weight of the square? Weight in the simple terms is m into g of the rectangle divided by m into g of the square. So what is mass? It is density into volume into g for the rectangle divided by density into volume into g for the square. We know that volume is equal to area into L, so it is rho into a into L into g divided by rho into a into L into g. This is for the rectangle and this is for the square. And the question they have clearly stated that the material is same, so the density will be same. We can cancel these two. They have stated that the length is same, so we can cancel out L, and g is also going to be the same. And what is left with is area of the rectangle divided by area of the steel, which is b into d divided by a square, right? And this is going to be b into 2b divided by a square. This will give 2b square divided by a square. This is equal to 2 into 0.63a the whole square divided by a square, and we will get it as WR divided by WS equal to WR divided by WS is equal to 0.7938. It's a very interesting finding. WR is equal to 0.7938. So if we cross multiply this, we can say that WR is equal to 0.7938 times of WS. What is the meaning of this? If you take a cross section, if you take a circular section, or square section and a rectangular section, which is made of same material and have the same length, which is carrying the same load and stress, then the rectangular beam will be lighter when we compare with the square, because the weight of the rectangle is only 0.793 times of the weight of this square section. So which one is advisable to be used as a beam? The answer is very straightforward. The answer is, for the same condition, rectangular beam is the most suitable one when we compare with the rectangular and the square. So that's the reason why we adopt the rectangular cross section for the beams. Majority cross sections are of rectangular shape. So this is a very interesting finding, and now if you go and inspect different beams, you can see that majority of the beams that is used as a cross section of rectangle. And this can change, but whatever might be the physical relationship between the breadth and the depth of the rectangle, still the rectangle is having the least weight when comparing with the square. In similar manner, when you compare the rectangle to the circle, we can say that it is going to be something different. Or if you can do the same kind of comparison with the square to rectangle, square to circle, like that, you can easily do the calculation. So this is how you have to carry out the comparison between the two different cross sections. So moving forward, we have another thing to compare, which is the strength of the beam. Strength of the rectangular, square, circular cross sections. When they have given that the material is same, load is same, length is same, and have the same area like this. So using the same area, you have to find out the physical relationship between the rectangle, square and the circle. And if they have asked us to compare the strength, So I have already told in the section modulus that if they are asked to compare the strength, we can compare the Z of R divided by Z of square. We can compare the Z of R to the Z of circle, or we can even compare Z of the square to Z of the circle. So this is what they have asked us to compare, and in order to compare this, we have to get the physical relations. So what is the value of A in terms of B, what is the value of diameter in terms of B, or what is the value of diameter in terms of A. This relation has to be obtained using the same area concept, like area of the square is equal to area of the rectangle. So A square is equal to B into D. So A square is equal to B to B square. So A is equal to root of 2 into B. Like this, you have to obtain the relation and you have to substitute it for the section modulus and get the comparison. So this is the common methodology that can be adopted for the comparative type of questions. So this is how we do the comparison. Now comes the design. How will we carry out a design of a beam? Designing purely means the size of the cross section for the particular loading condition. So if we look here, we can say that it's a simply supported beam. So it's simply supported beam which carries a mid load of how much? 100 kN, and the span is 3 meter, right? And what they have given is the allowable stresses, what? 250 megapascal, and the factor of safety is 2. So you have a factor of safety and stress. You have to find the allowable value as 250 divided by 2, which is nothing but 125 megapascal, and you have to use this 125 megapascal as the bending stress or the limiting value for the beam. And they have given that the rectangular cross section with depth is equal to twice the width. So how will you design it? It's very simple. Sigma is equal to m by I into y. When you substitute it, 125 equal to, you have to find out the moment. So how will you find the moment? Using the SFT BMD, you can easily calculate the relation. The value of reaction is going to be 50 kilonewton. So the bending moment is something like this, and the value is going to be 50 into 10 cubed into 1.5. So this is the value of m you have to use. So substitute the value for m, and I and y will be using this. So you can easily calculate the value of b. You simply substitute all these things and get the value of b, and can obtain the value of d. So this is how you design a. It's a simple question which is used for the design of beams with the basic terminologies. Okay, so kindly go through these questions and have a good understanding about the bending stresses and its distribution in the beams. So that's all for today's session. So see you with the shear stresses in the next session. So thank you.